Next up, we have Micah, who's going to tell us about our orbital torus imaging on fire.
Thank you. Hi, everyone. My name is Micah Oeur. I'm a second-year grad student at UC Merced, and I'm advised by Adrian Price-Whelan and Sarah Loebman on my project called Orbital Torus Imaging on Fire. This is still a work in progress, so I don't have conclusive results to show you today. However, my goal is to generate some discussion among a room full of awesome dynamicists. One of the fundamental goals of physics and astronomy is to understand the cosmological and particle physics properties of dark matter, since it's the main driver of structure in the universe. This is why so much effort goes into developing, implementing, and testing the tools that astronomers use to constrain the mass model of local group galaxies. Modeling methods exist, and they generally assume two things. They assume that the galactic gravitational potential is smooth and uniform. They also assume that the distribution function, the probability of finding a star in a given volume of phase space, is time invariant. We've known about satellite galaxies and perturbations to the Milky Way for a while now, but as we've seen in a lot of the beautiful talks from earlier this week, what's new is that we can detect them. Precise Gaia data have revealed fine-scale structure, which previously wasn't resolved for lack of data. And so this is really the first time that we're beginning to appreciate the extent of the disequilibria in our galactic disk. So the tools that we do have were developed in steady state, which is a condition that we now have ample evidence is violated in our system. And not only that, but traditionally these methods only make use of kinematic observations of the tracers when so much more information like chemical abundances, measurements of magnesium or carbon, for example, are available to us. So we have chemistry, we have positions, we have velocities. How do we leverage that? Well, I'd like to talk through some parameters. On the left, we're looking at stellar orbits in Cartesian coordinates. And so on the x-axis, we have z, distance from the midplane. On the y-axis, we have vz, which corresponds to vertical motion. We can view these stellar orbits in a different coordinate system, action angle coordinates, where the vertical action, jz, is a conserved quantity. You can think of it like an energy. It's an integral of motion. And the angle, theta, is phase, and it corresponds to where along the orbit you are. So thinking through different ways to view these stellar orbits is important to us because compared to some of the dynamicists in the room that work with planets, they can see planets move, but the orbital timescales that we work with are millions of years. And so we really only get a snapshot in time of kinematics. And so a big question for us is, what can we do with that? So I'd like to introduce you to some of the observational evidence that we see in the universe. We empirically observe that stars on higher action orbits have a different distribution of element abundances than stars on lower action orbits. And so looking at this plot from Price-Whelan et al. 2020, we can trace this trend of lower height, lower metallicity, higher height, higher metallicity for magnesium abundance. And how this connects back to the orbits I showed you. So going forward. How this connects to the orbits I showed you on the previous slide is that the level contours that we observe in the element abundance distribution in actions corresponds to the shape of the orbit of those stars. And so this is an informative constraint on the galactic gravitational potential because these element abundance distributions are functions solely of the vertical kinematics of the actions and not of the time-dependent phase or angles. And so this is why we expect to see a given shape of the orbit in the correct potential, because in the incorrect potential, that same stellar orbit would appear squashed, since altering the potential alters the space in which these stars traverse. And so it's in this way that orbital torus imaging combines stellar kinematics with newly unlocked chemical abundances from surveys such as apogee in order to constrain the dark matter distribution in our Milky Way. Since we have large amounts of survey data, we can compute these action angle coordinates for a large number of stars. and we know their elemental information. So using kinematics and chemistry, we can illuminate the structure of the matter distribution in our galaxy. So the FIRE cosmological zoom-in simulations will allow us to see how orbital torus imaging performs in a system which is realistic and complex, which has similar disequilibria to the Milky Way, but for which we know the ground truths of the mass distribution. And so I have access to 15 Milky Way-like galaxies for which we know these stellar birth positions, the ages, and the present day positions and velocities to be able to more cleanly test the reliability of this modeling method. The assumptions underlying orbital torus imaging require that the stellar system be in equilibrium, and the FIRE simulations have merger histories and substructure that challenge those assumptions in realistic ways. So some of the questions I intend to answer are, how well does orbital torus imaging recover the mass distribution of these FIRE simulated galaxies? How much disequilibria is this method sensitive to? And the FIRE simulations are the ideal test bed to investigate this. So on the right, we're looking at an analogous element abundance gradient for a FIRE simulated galaxy. And you'll note the same smooth systematic variation in action that we previously noted. So implementing orbital torus imaging in the FIRE simulations will allow us to be able to improve the modeling so that it can naturally handle the effects of disequilibria that we find in the simulations. This is my project trajectory. I'm currently developing simplified parametric models for the stellar, gas, and dark matter distributions of the FIRE galaxies, which I'm fitting to true particle positions so that we can be sure that they accurately describe our system. I'll implement orbital torus imaging using these parametric potential models by observing a part of the disk, which I'll choose by selecting a volume around the sun and then placing the sun at different locations within the galactic disk, as we can see from my very colorful top-down view of a FIRE simulated galactic disk. This will allow me to assess how much the disequilibria in the FIRE disks contribute to the accuracy of my parameter recovery, since I'll be able to compare the orbital torus imaging inferences to what the true parameters are. I've currently been working on fitting a Miyamoto Nagai disk model, which is just one particular simple axisymmetric disk potential model to the stellar component of a FIRE simulated galaxy. Here, my parameters are the total mass contained within a given radius, vertical scale length, and vertical scale height. We can see just by looking at these two plots that a Miyamoto Nagai profile using my best fit parameters seems to describe the stellar distribution pretty well. I'll also analytically fit the gas and the dark matter components. So in summary, we need a reliable way to constrain the galactic mass distribution that takes disequilibria into effect. Orbital torus imaging leverages kinematics and chemistry in order to do this. In order to assess the bias that this method has to disequilibria, I'm implementing it in the FIRE simulations, which includes quantifying the match between the simulation and the analytic description of the potential. My next steps include continuing to compute best fit parameters for my analytic form of the potential by fitting to the particle positions, as well as working towards checking to see if orbital torus imaging actually recovers the values that we expect for the parameters. Thank you so much for your attention and for the opportunity to present at the DDA.
Very much. We have time for at least one question. Yes.
This is super cool work, and I'm really excited to see where it goes. When you showed the fire, magnesium and iron, it seemed to have a much smaller dynamic range. Is fire not just not producing as big a range of metallicities? I'm looking at the color bars, basically.
Yeah, the color bars are different because our metallicities are definitely different from the true Milky Ways. Thank you.
Thank you.
One more quick one if you have. Yes.
Very nice. I was wondering if you're going to look at galaxies that have different degree of disequilibrium, just to calibrate how sensitive your methods are.
different fire simulated galaxies?
Yeah,
Yes,
with
of
different,
course.
such that they have different degree of disequilibria. So you
Right.
can
So
see.
some that are more quiescent and some that definitely have
Right.
violent merger histories.
Yeah.
Absolutely. I would love to look into that and